At the end of the last video, we left off with showing kind of an algorithm that we could use to find the greatest common divisor of two numbers. And that has been formalized into what we call the Euclidean algorithm, named after Euclid. He did enjoy number theory as well as working with a little bit of geometry. So here's kind of the formal description of the algorithm. I like to learn about it in terms of an example. So just running through the language, okay, we have two positive integers, and we say one is bigger than the other, or at least equal to, and then we have to find the GCD by this kind of process. Okay, so let's go through the process with an example. Okay, all right, so we have GCD of 31, 56, and 22 that we want to find. So what we have to do is name the bigger one A, the smaller one B, and then we go through and kind of start this process. Okay, we define A and B. We set this I, and I is really just a counter. You don't really need to keep track of it. But the idea is that we need to continuously do the division algorithm. So here we go. We're going to say 3156, and then we need to express this as 22 times a number, and then so I would take my calculator, do 3156 divided by 22. I get the whole part is 143, and then I would do 143 times 22, subtract that from 3156, and I get plus 10. Okay, so then I do have a remainder, and it says number 4, if the remainder is 0, you're done, and this 143 that I found would be the GCD, but as our R is positive, as our remainder is positive, we have to go through this process again. So now I take 22, my old B, which was my first remainder, if you will, and then I need to express it in terms of the new remainder that I found, R2. And so then I do that. Okay, 10 times 2 plus 2. Okay, great. Still don't have a remainder of 2, so I need to do it again. Now with writing 10 as 2 times a number, which is 5 plus 0. And so now I did get to a remainder of 0, so then the GCD, it is saying, is that last remainder that I found, so 2. So I'm saying GCD of 3156 and 22 is 2. Okay? So that's kind of the idea behind the Euclidean algorithm. And that has to do, remember at the beginning, with that theorem related, or that proposition related to divisibility. Okay, so now the rest of the video is going to be the proof of the Euclidean algorithm. It is described in the textbook. It is a little challenging to parse through, which is why we're going to do it in this video. Okay, so just keep in mind that that the Euclidean algorithm is a sequence of divisions with remainders. Okay, and what we know is that through this algorithm, we know that the RIs are strictly decreasing. Okay. Mainly because we're always removing holes from this and then leaving something at the end that is smaller. Okay, and we also know that when the algorithm reaches, or when the remainder reaches 0, the algorithm terminates. Okay, so there's a finite number of steps. Okay, just keeping all that in mind. All right, so remember, this whole algorithm is meant, or what we're trying to do rather, is trying to find the GCD of these A and B. Okay, so if we start with the GCD of A and B, okay, this part of the proof is actually kind of straightforward. So in terms of our terminology, what they actually call this, remember according to the structure of the proof, is R of I minus 1 and R of I. Because we started I is equal to 1, so this is kind of the process that we use. So that is just by definition. Okay. Then we're saying that, well, when we compute this, we can actually say that this is the GCD of Ri, comma, Ri plus 1. So after we've run the division algorithm once, the GCD of what we started with and the GCD of both B and the remainder there after from A and B is equal, and then this is true by the proposition. Okay, because remember, if D divides A and D divides B, then D divides the sum or difference of A and B. Okay, so that part is true. Okay, and then it extends. Okay, so then this part extends to, say, GCD of Ri plus 1 and Ri plus 2, and so on and so forth, okay, by the same proposition, okay, until eventually we get to GCD of, say, R, let's just pick T times, let's do this QT, the quotient, and then we would do R of T. Okay, so that's the last step. And that would result in a remainder of 0, right? So then all of this would just be R of T. Okay, so we're saying that all of these have the same GCD. I'll also add, just for clarification, according to this pattern, when we get to R of T, Q, and R of T, this would actually be R of T minus 1. Okay, but same idea, you're still taking GCD of successive remainders. Okay, and so this really is, and I maybe should say this is more like a sketch of the proof because I haven't included all the formal language, but the ideas are here. We've shown that the GCDs are all the same. We have shown that, and we've said that the RIs are strictly decreasing, and then so this does imply that the algorithm does terminate. Okay, because eventually, if you're always decreasing, we can only decrease to 0 in this case. So these are the two main ideas. Now in the textbook, they do include in their proof a little bit about some phrases on the efficiency of the algorithm, and I'm not too concerned about that. Feel free to look that over if you're interested, but I'm not going to worry about it right at this point. Okay, so big ideas here. Euclidean algorithm can be used to find the GCD of two numbers. We went through an example, and then at least the ideas behind the proof. Okay, really making use of that proposition.